Alright, so in this part, our objective is to systematically develop the rules for operations with numbers, relations among numbers, and the properties of these operations and relations, such as addition, multiplication, inequalities, positivity, square roots, nth roots, and so on. And examples of properties would be commutativity, associativity, distribution, etc. Now, this objective is motivated by the fact that we find many of these properties frequently recurring throughout mathematics, applying to a variety of objects, including complex numbers, functions, or mappings. And it's worth noting, for example, that in the particular case of functions and mappings, commutativity does not hold in general, as it does with simpler structures, such as numbers and so on. So for example, suppose you have two functions, f and g. Now what is meant is that the order in which you compose two functions, i.e. apply one after the other, matters. And the result will typically be different depending on that order. In simpler terms, if you have two functions, f and g, then f of g of x is not always the same as g of f of x. So it's always an interesting problem to determine when commutativity, for example, holds and when it does not. So the rules of algebra are used in most, if not all, branches of mathematics, including the study of geometry, for example, in computing dimensions of figure and form, distances, etc. This associates numbers with geometric objects, and thus algebra with geometry. Chapter 1. Numbers. The primary aim of this chapter is conditioning oneself to having efficient reflexes in handling arithmetic operations and extending intuition for the rules governing them. So it's good practice to motivate algebraic perspicacity via geometry, but still we must develop, as mathematicians, perceptive cognitive reflexes and rigor in symbolic calculation, especially with regards to simple problems involving, say, linear equations or a quadratic function of sorts. So the Foundation's pedagogy of mathematics is mainly concerned with the extensibility of mathematical systems, starting with how do basic arithmetic operations interact with particular number systems in some specific context, and then extending the findings to a more general context. Let's have a look at some examples. So for instance, for the equation 2x equals 3, there exists a solution S in the set of rational numbers, but not in the set of integers. For the system of equations x squared equals 2 and 10 to the power of x equals 2, there exists, respectively, some solution s sub I in the set of real numbers, but not in the set of rational numbers. In this final system of three equations, namely x squared equals minus 1, x squared equals minus 2, and 10 to the power of x equals minus 3, there exists, respectively, some solution s sub j in the set of complex numbers, but not in the set of real numbers. Now, some of you will rapidly recognize these observations as tautological, and others may still need to develop that insight to be able to see this quickly or to work it out without error. So this methodology of extending one system of objects to a larger system is really at the core of the mathematical sciences, from the foundations all the way up to the most advanced contexts. And so we are going to devote a good amount of time to the development of this acumen. Section 1. The integers. Let's start with some basic terminology and set notation for number systems. We have the positive integers, also known as the natural numbers or counting numbers, 0, naught, null, and some common numerals representations of 0. I've snuck in this representation of 0 as the truncated set of whole numbers, which is my way of indicating that I subscribe to the notion of 0 as more of a pseudo-number or concept that has an inverse relationship with infinity. But I'll have more to say about this later. And finally, we have the empty set, not to be confused with the set containing an empty set. We have the prime numbers and the negative integers. And lastly, a number line to visualize these sets. Right, so in the following discussion, we'll be referring to these kinds of numbers and 0, and in later sections, we'll extend our results to increasingly complex systems. So let's continue by listing some basic postulates or axioms of algebra. which together with the definitions above provide a sound basis for mathematical reasoning. Axiom 1. The additive identity, namely 0, added to any number equals that number. Axiom 2. The additive inverse of any number a added to that number equals 0. And then we give the conjunctive normal form. So in the geometrical representation of the integers, this means that a and minus a take on opposing sides relative to the origin, as shown in figure 2 below. It follows, according to this representation, that we may now express the notions b equals minus quantity minus b, or c equals minus quantity minus c, where b and c are integers. To illustrate these special cases, we can diagram the pictures below. And so another way to think about this linguistically is simply that the opposite of minus b is not minus b, and the opposite of minus c is not minus c. So it's good to make this use of terminology minus a as opposed to negative a explicit, where negative a suggests that minus a is a negative number. This is only true when a itself is a positive number. Perspicuously, we see that 2 equals not quantity minus 2 is a positive number. But 2, in the case above, is equal to minus a, where a equals minus 2. And a itself, in this case, is negative. So however labyrinthine the veneer of this remark, this fact constitutes arithmetic law and should be internalized. Section 2. Rules for addition. Axiom 3. Commutativity. If a and b are integers, then a plus b equals b plus a. Axiom 4. Associativity. If a, b, and c are integers, then a plus b quantity plus c equals a plus quantity b plus c. Theorem 1. If a plus b equals 0, then b equals minus a and a equals minus b. Or in simpler terms, we might say that if a is the additive inverse of b and b is the additive inverse of a, then a plus b equals 0. To prove this statement, we simply add minus a to both sides of the equation, a plus b equals 0. We get the following statement. And since, by the rules of arithmetic, minus a plus b equals 0 plus b, which equals b, by inference, we find that b equals minus a. QED. And as a special case of Theorem 1, we have for any integer a, Theorem 2, the double negative multiplicatives property, or the double negatives property. Namely, a equals minus 1 times quantity minus a. Right. So Theorem 2 follows from Axiom 2, the additive inverse, and Theorem 1, where minus a is substituted for b. And we can see this somewhat easily by starting with the additive inverse and subtracting quantity minus a from both sides of the equation. And in doing so, we immediately obtain the double negatives property, which again, in this form, states one of the consequences of Theorem 1. And let's notice that this formula is true whether a is positive, negative, or 0. If a is positive, then minus a is negative. If a is negative, then minus a is positive. Now, similarly, from these rules of operation, we can derive the distributive property of minus as a corollary, which formally states that for all a and b that are integers, minus quantity a plus b equals minus a plus quantity minus b, which logically implies minus quantity a plus b equals minus a minus b. And so, by the way, just as a reminder, A corollary is a proposition that follows from and is often appended to one already proved. So in this case, our corollary follows from theorems 1 and 2. Another way to think of it is as a direct natural consequence or result of something else. And so we want to show that the distributive property of minus follows naturally from theorems 1 and 2. Right. So per theorem 1, if x and y are integers, then x equals minus y and y equals minus x implies that x plus y equals 0, which is to say, formally or symbolically, x equals minus y and y equals minus x implies that x plus y equals x plus quantity minus x, which equals 0. So to prove the assertion of the corollary, we can simply assign quantity a plus b to the indicator x and quantity minus a minus b to the indicator y, and we'll set the sum x plus y to 0. Perfect. Next, we can remove the quantizing parentheses by associativity Then we can group like variables by commutativity and after performing the correct subtractions, we end up with 0 plus 0, which equals 0. And we're done. This proves our corollary. Axiom 5. If a and b are positive integers, then a plus b is also a positive integer. Now we simply assume this rule to be self-evident regarding the positive integers, and also regarding the positive real numbers. Theorem 3. If a and b are negative integers, then a plus b is negative. Now theorem 3 we can prove simply by letting a equals minus m and b equals minus n, where m and n are positive. Then a plus b equals minus m minus n, which equals, by the distributive property of minus, minus quantity m plus n, which shows that a plus b is negative because m plus n is positive. And we're done. So in the next video, we're going to work through the problem sets for sections 1 and 2 of chapter 1. I'll see you over there.